Now we take what we know about linear inequalities in two dimensions and apply it in a scenario where we want to optimize something called an objective function. So optimizing means maximizing or minimizing, right? Finding the best of in either case. So we're gonna start with an example of what one of these problems might look like, and then I'll discuss the concept of this and why it works the way it does, and then we'll proceed to solve the problem. So let's look at this. Let's do this. Find the maximum, and we're going to do both in this example. Find the maximum and minimum values of the objective function and let's look at the objective function p equals 10 minus x minus y. So before we proceed with a question, the objective function depends on both x and y. It's a function that depends on two values, okay? So the idea for finding the maximum and minimum is to find the appropriate x and y to plug in here to make p the biggest value and to make p the smallest value. All right, I forgot to mention, notice that I'm doing this on graph paper. There will be quite a bit of graphing, so I recommend that you have some if you're taking notes. All right, so find the maximum and minimum values of the objective function p equals 10 minus x minus y. And so there is no limit as to how big p could be currently. So what we have to do is put some constraints on this objective function. So with the following constraints. And our constraints will be constraints on x and y. And particularly they will be given in the form of a system of inequalities. So the first one we'll have is 2x plus 3y is greater than or equal to 14. Then we have x minus y is greater than or equal to negative 3. Then we have 4x plus y is less than or equal to 18. So those are the constraints on x and y, and we need to use those constraints to figure out, based on the solutions here, the x and y solutions to this system, what's the largest and smallest value of this objective function p. All right, so here's the concept now. I'm going to switch over to a program called GeoGebra. I've put together an animation to show you. So the first thing we're going to do is I have graphed the solution set to the system. I've graphed the constraints, okay? So this is what we get. This is a graph of the constraints in two dimensions. You end up getting this triangular shape, and you get all the points inside. This region here, this triangle and everything inside are the solutions to the system of inequalities. And we need to figure out which ordered pairs here make our p, our objective function p, the biggest and the smallest. So how does p relate to this graph? Well, the thing is, when you introduce the objective function, which is a function of x and y, you take this two-dimensional system and you turn it into something that's three-dimensional, as you can see here. So our constraints are graphed now just on the xy plane, but now you've got a z plane, or really it's a p plane, p-axis, because our objective function is called p, but commonly it's x, y, and z, okay? But now we can see our constraints graphed here. So what does the objective function look like? Well, I've got that here. Let me turn it on. The objective function is a plane also, but it's in three dimensions. So let me kind of swing this around a little bit so you can get your orientation. So you see that plane there, that's the objective function. That's how you would graph that objective function. It's a plane in three dimensions, okay? So if we come back, the plane that I talked about is this objective function, and the triangle are the constraints, okay? Now, how do I use this triangle to find the maximum and minimum of that objective function? Well, really what happens is when you look at this in three dimensions, this triangle actually is a prism that goes on forever up and down. And so what happens is it cuts through this plane. So let me turn that on. I've called it a projection here. If I project this this set of constraints onto the objective function, we get this mirror image of, and I'm looking at it from above so you can get an idea of what I'm talking about. You can see it's projected up through the plane. We get this projection onto the objective function. And you can now see, hopefully, that when we talk about the maximum, sorry, it's kind of going wonky here. When we talk about the maximum on the objective function, we're talking about the highest point. So you can see that this vertex of our constraints, that x and y value will yield this point on the objective function plane, which is the highest point. And this point back here on our constraints, right? Let me see if I can do this without making it jump all over the place. Didn't have too much luck there. But this point yields this lowest point on our objective function. So this xy is going to give us our lowest, our minimum value of the objective function. Now the point of all of this is these constraints have every point on the boundary lines and every point inside. But really, all that we need to look at to find the max and min of our objective function are the vertices of the constraints of the system. So when we solve our system to get this triangle, and then we try to figure out the maximum and minimum of our objective function, all we're going to do is plug in the vertices x and y coordinates to the x and y of our objective and figure out which is the highest. So I know if you're taking notes that this picture is difficult to draw. You may want to just try to draw something like this, or snap a picture and put it into digital notes or something. But the point of the animation is to point out, and it's often glossed over. I don't know if I've ever seen it mentioned in a textbook, but we look at just the vertices of the constraints to get to maximize or minimize an objective function. That's the point. All right, now let's get down to business here. Let's actually graph our constraints so that we can find the vertices and then plug them into the objective function. Luckily, we don't have to graph anything in 3 dimensions. So let's set up the plane. Let's see here. We'll set up the plane over here. All right. And we need to graph our constraints. And all of these have equals in the inequalities, so they're going to be solid lines. Now, the easiest way to graph all 3 of these is to use intercepts because they're in standard form. So let's look at the first inequality. 2x plus 3y is greater than or equal to 14. And let's find the intercepts. So if I plug in 0 for x, I get 3y equals 14. And if I solve that, I get 14 thirds. And I know I'm going to have to graph this, so I'll think of it as 4 and 2/3 as a mixed number. If I plug in 0 for y, I get 2x equals 14, so x is 7. Okay, so we'll plot this later. I'm going to wait to kind of see what scale I'll need on my axis before I graph anything. So let's go ahead and find all of these intercepts. Let's move this over. All right, the next one is x minus y is greater than or equal to -3. And this one's a little bit easier. If I plug in 0 for x, I get -y equals -3. If I divide, I get +3 for y. If I plug in 0 for y, I get x equals -3, and that's all we have. Okay. And then let's do the last one, 4x plus y. Let's see, let's go up here and do that, just so we're on the screen. 4x plus y is less than or equal to 18. If I plug in 0 for x, then y is 18. If I plug in 0 for y, then x would be 18/4 or 9/2, which is the same thing as 4.5. Okay, so the biggest value that we have here is 18. So that's a y value. Let's go ahead and move our x-axis down, actually. Oh, if it'll let me. Let's see here. There we go. Yeah, that might be good. We'll put it right there. Actually, I think what we'll do is we'll go by 2s. Yeah, we'll make our scale by 2s. So let's start plotting these. Let's graph the boundary line. So 0, 4, and 2/3. So this is 2. So there's 4. This is 5. So 4 2/3 is right there. And then 7, 0. This is 2, 4, 6, 7 would be right there. Let's graph that boundary line. Use a straight edge if you have one, just to keep things kind of clean, because this gets a bit clunky. All right. Now let's label the boundary line equation. So this was the one for 2x plus 3y equals 14. And we have to know where to shade. So we're going to use the origin. We're going to plug in 0, 0 for y. So 2 times 0. We're plugging 0 in for x, 0 in for y. And we want to know if that's greater than or equal to 14. So when we simplify the left side, we get 0. And 0 is not greater than or equal to 14. So here, we're not going to shade the 0, 0 side. I'll just make a note of that. So that means we're looking at everything kind of above this line. And you could even write above in there if you want. Okay? All right, the next one, we'll do the same thing. Plug in 0, 0, so we get 0 minus 0. We want to know if that's greater than or equal to negative 3. Well, 0 is greater than or equal to negative 3, so that's yes. So we will shade the 0, 0 side of this guy. Now let's plot the points. I forgot to do that. 0, 3 is right there, and negative 3, 0 is right there. And we'll connect those points. Something like this. Okay. And let's label that boundary line, which is x minus y equals negative 3. And on this guy, we do want the 0, 0 side. Okay. So we'll shade everything below. So right now, we're shading everything up here and everything here. So right now we're left with, if we look at that, right now we're considering this part over here. Okay? Keep that in mind. The last one we'll do the same thing, plug in 0, 0, so we get 4 times 0 plus 0. Is that less than or equal to 18? And the answer is yes, because 0 is less than or equal to 18. So that guy, we're going to shade the 0, 0 side. Let's plot our points. So 2, 4, 6, 8, 10, 12, 14, 16. Here's 18. So 0, 18 is there. And then 4 and a half, 0. So 2, 4 and a half is right. There's 5. So 4 and a half is like right there. And let's graph that. Okay, so it looks something like this. And that boundary line equation is 4x plus y equals 18. Now I apologize for how cramped this is. Hopefully if you're using your own paper, you're spreading things out. I'm just trying to fit as much on the screen here as I can without being too messy. All right, but this guy, we decided that yes, we will shade the 0, 0 side. So remember, what we had before that was everything here, right? And now what we have is everything that's in there on the 0, 0 side. So we're looking just at this little bitty triangle now. So that's our final shaded region, okay? So our final shaded region is everything in this triangle. And remember from the animation I had before, it was a triangle that looks something like this. We just have to now find, remember the point of the video was to find the vertices, and there are 3 of them. We can see that this shaded region has 3 vertices. And because the graph didn't quite work out like really nicely, we probably need to use algebra to solve for those vertices. So let's look at vertex A. So vertex A is where this line, x minus y equals negative 3, intersects this line, 4x plus y equals 18. Okay, so A is where we have x minus y equals negative 3 and 4x plus y equals 18. We need to figure out where those intersect, so we need to solve this system. The easiest way to solve this particular system probably is by elimination. So what we'll do is we'll add the 2 inequalities together. Again, you should already know how to do this, but we'll add these together because the y's are going to cancel. So we get 5x equals 15, and now y is gone, so we can solve for x, and we can see that it's 3. So x is 3, and then we need to figure out y. So we can plug this x value back into either one of these equations. I'm going to choose to plug it into the first one because it looks like a simpler equation to me. So 3 minus y equals negative 3. And now we can solve this for y. Subtract 3 over and divide by negative 1, and we can see that y is 6. So vertex A is the ordered pair where x is 3 and y is 6. Let's see if that seems reasonable on our graph. So here's where x is 3. That seems like a reasonable x-coordinate. And here's where y is 6. So yeah, that seems perfectly appropriate. So A is the vertex 3, 6. Now let's look at vertex B. B is where the 4x plus y equals 18 line intersects the 2x plus 3y equals 14 line. So we need to figure out where those intersect. So we've got, let's see here, 4x plus y equals 18, and we have 2x plus 3y equals 14, and we need to solve this system. So now, unfortunately, if we add these together, nothing cancels, but we can easily multiply the second equation, both sides, by negative 2. And that's going to give us, well, we still have our 4x plus y equals 18, and then we have negative 4x minus 6y equals negative 28. Now when we add those together, the x terms cancel, and we get negative 5y equals negative 10, which means that after we divide, we can see that y is 2. Then we can plug this y value back into either equation. I'll plug it back into the first one. Doesn't matter which one. So 4x plus 2 equals 18. Subtract the 2 and divide by 4, and we can see that x is 4. So vertex B is the ordered pair where x is 4 and y is 2. And we'll see if that's reasonable. So x is 4 is right here, that's good, and y is 2 is right there, good. So we may have guessed that that was 4, 2 anyway, without doing any algebra. All right, last we have to do vertex C. Vertex C is this point right here, which is where 2x plus 3y equals 14 intersects x minus y equals negative 3. So let's solve that system. So we have 2x plus 3y equals 14, and we have x minus y equals negative 3. Now, nothing cancels if we add all of that together, so we have to do a little manipulation here. Let's multiply the second equation by 3 on both sides. And so we get, our first equation didn't change. Our second equation turns into 3x minus 3y equals negative 9. And now the y's will cancel, leaving behind 5x equals 5. And dividing by 5, we can see that x is 1. Now this is working out very, very nicely. We're getting integers everywhere. But you can see, like, if this 5 here were a 6, you'd get a fraction, and that can totally happen. So don't assume that you're always going to get nice values here, okay? But they're just numbers. You can deal with them. All right, so if x is 1, we plug that back in. I'll plug it into the second equation to solve for y. So I get 1 minus y equals negative 3. Subtract the 1 and divide by negative 1, and we can see that y is 4. So vertex C should be the ordered pair where x is 1 and y is 4. Let's go look at it. So here is where x is 1. That's good. And here's where y is 4. So that looks very reasonable. Okay, excellent. So now we have our objective function and we have the vertices of our constraints. Now this region here, these set of constraints in this type of problem is often called, this region is often called the feasible region. Okay, so we have the vertices of the feasible region, we have our objective function, and now we need to use the vertices to find the maximum and the minimum values of this guy. Again, oftentimes you'll just be asked to find the maximum or the minimum, but for this video I want to make sure we look at both. So let's see here. Let's grab all of this so that we have it, so we can reference it. I'll copy it and paste it. You can rewrite it down here somewhere if you need to. Okay, so that's That's going to make it easier for us to reference this. So now what we need to do, and actually I don't even need the system, right? So I've got my objective function, and I've got my vertices 3, 6, 4, 2, and 1, 4. So now I just need to plug these x and y values into my objective function. So if I plug in 3 and 6, I get p equals 10 minus x, which is 3, minus 6, which is, or minus y, which is 6. So 10 minus 3 is 7, minus 6 is 1. So this vertex gives us an output of 1 in our objective function. For 2, let's create a little more room here. For 2 gives us p equals 10 minus x, which is 4, minus y, which is 2. So p equals 10 minus 4. 6 minus 2 is 4. So this gives us a bigger output of our objective function. And then last we have 10 minus 1 minus 4, which gives us 5. So we can see that when we compare all the outputs of the objective function at the corners of our feasible region, we can see that 5 is the max value of the objective function p. And if we want, we can be even more precise, and it occurs at the vertex 1, 4. And I don't think that fits on the screen. Let me move that over. Okay, so 5 is the maximum value of the objective function. It occurs at 1, 4. And then we can also see that 1 is the minimum value of the objective function, and it occurs at the vertex 3, 6. And that is how you might answer that question. Now, the problem didn't specifically ask us to name where you attain the max and min values. So you might just say 5 is the max and 1 is the min. That'd be totally fine with the way the instructions were worded here. But it doesn't hurt to be more precise, and that's what we've done here. So anyway, hopefully the animation helped you understand how to visualize this in 3 dimensions, so that you know that once you get your feasible region, all you need to do is find your vertices, the corners of that feasible region, and plug them into your objective function to see which one gives you the highest or lowest output.